Okay, so this is a problem dealing with mixing two phases together and finding the final temperature, okay? We're still going to be using MS delta T, and we'll be using heat of fusion, because in this problem what we're doing is we're putting an ice cube, and we know its temperature, into a glass of water, and we want to know what the final temperature of the water is going to be. So basically the ice cube is going to melt, and the water is going to get colder. So the heat goes from the water to the ice cube, and you end up at a final temperature. All right, so here's the problem. If 25.0 grams of ice at 0 degrees Celsius, so the ice is at 0, so all we have to do is melt it, so delta H of fusion for the ice, and then take the temperature up to, or put heat in to end up at some final unknown temperature. So if 25 grams of ice at 0 degrees Celsius is placed in a glass with 250 grams of water at 25 degrees Celsius, to what temperature will the liquid water cool? So the way I approach this, just like I did with the previous problems in the other videos, I draw a little line and I say, okay, my ice is at 0 degrees Celsius. My water is at 25 degrees Celsius. What has to happen? Well, the ice first has to melt. So you have to do the delta H of fusion. So that's one step. And then you have to go from 0 all the way to some unknown temperature, T. So you have two steps for the ice, melting and then going up to some unknown temperature. The water, on the other hand, all it has to do is go down to this temperature, okay? So you make the two equations equal to each other and you solve for T. So the heat lost by the water is equal to heat gained by the ice, right? So heat lost by the water is equal to heat gained by the ice. Okay, so what is the heat lost by the water? MS delta T. The mass of the water is 250 grams. I'm putting a dot here so that we have 3 sig figs. The specific heat of water, they've given it to us to 4 sig figs, so we'll go ahead and use that. 4.184 joules per gram degrees Celsius. And the delta T is 25 minus T. We don't know what that final temperature is. So 25 minus T. Okay. Then what's over on this side? Well, first you have to melt the ice cube. So the ice cube is 25 grams. And then you multiply it by its delta H of fusion. So it's 334 joules per gram. But you also have to add that to, because remember, now the ice cube is melted, but now it has to go to this final temperature. So you do the 25 grams times, now it's liquid water, MS delta T, 4.184 joules per gram degrees Celsius. And then the delta T here would be T minus 0. T minus 0. Okay? This one was 25 minus T. You always have big number minus small number, okay? So 25 is definitely bigger number than what your final temperature is going to be. But T is going to be bigger than 0. So, all right, so you crunch the numbers, get everything on this side. Hopefully you remember how to do algebra. So it's this times 25, and then this times minus T. So you're going to have two things over here. So let's crunch the numbers here. Let's see what we've got. On this side, we have 26150 minus 1046T. That's what we have on this side. equals, and then after we've added all this, so this times this, get a number, and then we're going to be adding it to, and then this thing over here, this times t, and then just ignore the 0 because this times 0 is 0. So on this side, you're going to have, let's see if I've got anything here that I did. Let's see. I can't find what I have here. What did I have on this side? I have, this is 8,350. Okay, and this is all joules, by the way. This is all going to be joules. Yeah, grams cancel. The joules will eventually cancel. Eventually, everything cancels except for your temperature, which is T. Okay, so 8,350 plus, what do I have here? I have the 25 times this times T. So you end up with 104.6 T. So this is 26,150 minus 1,046 T is equal to 8,350 plus 104.6 T. Hopefully you can see all that and you're not confused. Okay, so what I would do is I would bring this over to this side. So 26,150 minus 8,350, and then bring this over to this side, 1,046 T plus 104.6 T. You end up with 17,800 on this side. So this minus this, you get that. And then on this side, you get 1,150.6 T. I double checked my math, so everything should be fine, guys. And then you say T is equal to, so this divided by this, and to 3 sig figs, you have 15.5 degrees Celsius. So your final temperature that the water reaches when you cool it off with that ice cube is 15.5 degrees Celsius. Okay, so honestly, the thing that trips people up with a problem like this is just the algebra, when it really shouldn't. Most of you are in super advanced math, so you've probably forgotten your basic algebra. So hopefully you can manipulate your equation easily and have no problem. All right, so we're done with all of this stuff, and we're ready to move on to the Clausius-Clapeyron equation. I have a couple of different problems to show you with the Clausius-Clapeyron equation, but first let me write the lovely name on the board and write the equation and tell you what we use it for, and then we'll go from there. So Clausius-Clapeyron equation. Clausius-Clapeyron equation. EQ just stands for equation, okay? Clausius-Clapeyron equation. Let me get a better pen, hopefully. All right. So this is going to have vapor pressure and delta H of vaporization and temperature. So this is the equation. Natural log of vapor pressure 2 over vapor pressure 1. Remember the natural log button, not log, ln. So get your calculators. You're going to be using the ln button. Is equal to delta H of vaporization over R. The R that we're using here is the universal gas constant, but the units we're going to use is joules per mole Kelvin. And that number will be given to you. That R is 8.31 joules per mole Kelvin. That's the one we will be using. Okay. 1 over T1 minus 1 over T2. Now let me explain what all these things are. This is, if you know the temperature and vapor pressure of a substance, and you want to know the vapor pressure at another temperature, you can use this equation. So let's say we have the delta H of vaporization of some liquid, and we know the temperature in Kelvin and the vapor pressure. So P1, T1, think of it as initial vapor pressure and initial temperature. So you have the initial temperature, you have the initial vapor pressure, you have the delta H of vaporization, and you want to know the vapor pressure at another temperature. So you have this, 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 you can solve for this. Okay, that's one type of problem. Another type of problem deals with, okay, you have the initial vapor pressure and the final vapor pressure, the initial temperature and the final temperature, but you want to find delta H of vaporization. You don't have the published value, you want to calculate it. So knowing the vapor pressures and the temperatures, and this is a constant, you can get delta H of vaporization. Another type of problem could be solving for the temperatures. So you have this, you have this, you have this, you have one of the temperatures, and then you solve for the other temperature. So those are the three different types of problems. I'll do maybe a couple of them, and you should be fine with these types of things. All right. I think I have, I can't see how many problems I've got, but all right. Main thing, know how to use your calculator, okay? Know how to use the ln button, know how to use the e to the x button. I think I'm going to write the problem on the board and then wait till the next video to actually solve it. So I'll have a couple of problems for you guys. In the meantime, get those calculators ready, and we'll do the Clausius-Clapeyron equation in the next video.